Okay, so I have here enclosed pipe. Look at this. If you're going to analyze the velocity and the pressure, see? So for 1.6 velocity meter per second, the pressure is 126 kilopascal. Now, if I increase the velocity, and that is by changing the dimension here, so the fluid here becomes faster, look, the pressure decreases. That's Bernoulli's equation, as I've discussed in the previous video. If the velocity is high, look at the velocity here. It's definitely higher, 6.2 than 1.6. The pressure is low. Here, the velocity is low, the pressure is high. Okay, so that's another way to explain Bernoulli's equation. Okay, now let's proceed to one of the important application of Bernoulli's equation, and that is Torricelli's equation. So look at the water tank here. So it is applied in the water tank. So basically the problem of the Torricelli's principle is we need to find the velocity of this fluid at the bottom of the water tank. And then how is it related to the water level? Look at this. Here's the velocity. If I decrease the water level, look at the velocity. Oops, it's open. We have to close it. Look at the speed. If the water level, or if the velocity, no, if the water level decreases, look at the velocity. It also decreases. Okay? So we need to find how is that velocity related to the water level. Okay, so this is, let's say this is your water tank. So we are at some height. So let's say you have the y1 here as the height. We have y2 here. And basically the difference between the two is your h, the height. And let's say what's the velocity here? So let's say this is your point 1 and P1. This is your point 2, P2. Okay. Now, if we get to analyze the demonstration earlier, as the water goes down, the velocity there, V2, is actually almost equal to 0. So that's the assumption here. We can assume the velocity of the fluid as it goes down is almost 0 as compared to the velocity of the fluid below. Okay, so this V1 is pretty much higher than the velocity at P2. But take note, we are in an atmosphere. So P atmospheric pressure equal to P1 equal to P2. So we're exposed to the atmosphere, or 1 atm, 1 atmospheric pressure. That is, if you remember, 1.1, I think 1.01. No, I think this is wrong. 1.013 times 10 to the 5 Pascal. That's the atmospheric pressure. And P1, P2 is the same. V1 is different from V2. V2 is almost 0, almost at rest. Okay, so let's apply Bernoulli's equations. We have P1 plus 1/2 rho density V1 squared plus M, no, not M, but density G Y1 equals P2 plus 1/2 density V2 squared plus rho GH or G rho GY2. Okay, so here the velocity 2 is almost at rest, so we can cancel that out. So this is 0. Okay, you follow? And the pressure are the same, so if you're going to transfer one to the other, they will just cancel out. They're the same, so we can cancel that out. Okay, so what we have will be, so what we have here is 1/2 rho V1 squared, and then I'll transfer this to the other side, equals density GY2 minus density GY1. Okay, but take note, you can factor out density times G. So H is equal to Y2 minus Y1 from here. Okay, I hope you follow. So this becomes 1/2 rho v1 squared rho g y2 minus y1, which is actually your h, right? So you can even cancel out density now. It doesn't change, so you can cancel out density. So what you are left is v1 squared equals transpose that 2, cross multiply 2g, and this is h, okay? And the velocity, we call it the efflux velocity. I will now remove sub 1, just call it v, is equal to the square root of 2gh, and that is the Richarlis theorem, or this is commonly called the efflux velocity. Okay. Oops, what's going on? So this is your efflux velocity. So basically, the speed of the water in a piping or in a water tank depends on the height. Look at this, the height squared. So if your height is low, the velocity of the water is low. So let's say you have a water tank and you're living in the first floor. Let's say you are in a dormitory or a student. You're living in the first floor. The velocity there is very, very high, according to Torricelli, of the water. But if you're the third floor of the dormitory, the velocity, oh, very low. So you have to wait for a longer time, okay, if you are going to take a bath. So I've experienced that as well when I was a student. Sometimes the velocity of the water in the third floor, I live in the third floor, is very low. Okay, so that ends our topics on fluid mechanics, that is fluids at rest and fluids in motion. So I hope you've learned something today, and I hope you can use it in your review for your NMAT or National Medical Admission Test, or for other competency in physics or other physics course that you can use. Okay, bye-bye. See you in the next topic of physics. Hopefully next week. Choose.